All right. Hi, everybody. So thank you, Giles. Thank you, everyone, for having us today. So our team at the Census Bureau has collaborated with Tumult Labs to explore ways to balance the need for accurate statistics while protecting respondents' confidentiality in order to develop a proposal for producing 2020 census data for detailed race and ethnicity groups in American Indian and Alaska Native tribe and village populations in our 2020 census detailed demographic and housing characteristics file A. It's a mouthful. It's also known as the detailed DHC-A. So our proposal for producing 2020 census detailed race and ethnicity group population counts and characteristics data focuses on tables that have been developed in an attempt to balance confidentiality requirements and the programmatic, legal, and statistical needs of our data users and our stakeholders. External partner feedback combined with our review of table access rates and our subject matter expert knowledge has informed the development of this product. And we're planning to produce data for more detailed race and ethnicity groups than we ever have before, but at many fewer geographic levels, as well as fewer and less detailed tables to balance accuracy and confidentiality. Our highest priority at the Census Bureau is to provide the most accurate data possible for the critical statistics needed by detailed population groups. So what is the detailed DHC-A? This is the data product where data users will be able to access data on detailed race and ethnic groups like Chinese, Mexican, Lebanese, the Navajo Nation, and many, many, many more. We're also planning to provide statistics on sex by age for detailed race and ethnicity groups. Not all groups will receive sex by age data. This will also be determined based on the size of the detailed group in a specific geographic area. Some data users have asked us to include lower levels of geography for places like cities and towns, and also for census tracts. So we're evaluating the feasibility of including these and adding them to the list of geographies we're already planning to produce data for, which includes nation, states, counties, and American Indian, Alaska Native, and Native Hawaiian areas. And through our ongoing engagement with the public and any use cases that they provide to us, we've been able to learn more about the critical needs for these data, which has led us to the decision to prioritize this product over some of our other data products. And this product is planned for release next summer in August of 2023. As I mentioned, our highest priority is to provide the most accurate statistics for critical data needs, especially knowing that these statistics on detailed race, ethnicity, and tribes, they're not available anywhere else. We don't have any other products with these data. So our research goals when developing this product were to explore how privacy and accuracy levels can be established to produce statistics on our nation's myriad population groups, to find ways to allow for equity across all major race and ethnicity categories, and strive to provide the same amount or more data than we provided from the 2010 census. Through our ongoing engagement with the public and the use cases that many of them have submitted, we've been able to learn more about the critical need for these data. This feedback has led us to the decision to prioritize this product over some of our other products. And we've also heard from data users that it's important to have data on detailed race and ethnicity at additional levels of geography, like census tracts and places. So as I mentioned, we're beginning to evaluate if it's feasible to include these additional levels of geography while still protecting respondents' privacy and providing accurate statistics. We'll have an ongoing dialogue and iterative feedback loop with stakeholders and data users about this work as our development plans evolve. We've heard from data users and we understand the critical need for these data. This summer, we're continuing developing and testing to incorporate data user feedback. And as part of our ongoing development and testing, we're examining whether accuracy targets we set are being met. Next year, in January 2023, we plan to produce a prototype demonstration data product using 2010 census. This data for the detailed DHC-A and the census data. We'll ask for public feedback and take that into consideration as we fine-tune the parameters and plans for our final product. And before moving into the production phase, we'll have additional engagement with stakeholders and partners and conduct tribal consultations as we work to produce these 2020 statistics for our nation's diverse communities. I really appreciate you having me today, and now I'm going to pass it over to Sam to talk about the differential privacy algorithm for how we will produce this product.
Great, thanks, Rachel. Hi, my name is Sam Haney. I'm a scientist at Tumult Labs. And in this section of the talk, I'm going to talk about the differential private algorithms that we at Tumult developed for this problem in collaboration with Rachel's team. So before I start, I need to show you this disclaimer. Tumult has been contracted to develop an algorithm, but the census has not yet chosen to use this algorithm, and any of the numbers I present during this presentation are not going to be used in production. They're just for illustration. Okay, so here are the two main takeaways that I want you to get from this section of the talk. First, that this privacy utility negotiation takes time and effort, both from the side of the DP experts to understand the fitness for use requirements, and from the domain experts, so Rachel and her team, to understand what knobs are available for them to tune the privacy loss fitness for use trade-off. And then second, I'm going to tell you about some of the specific tools and techniques that we used that might be helpful in your own applications. And I'll start with the former. So Rachel did a good job of presenting what this looked like from the census side, so I'm just going to briefly show you what this looked like from our perspective. Okay, so here's an overview of the design process. We started by understanding the problem and some preliminary fitness for use requirements. We designed a rough algorithm, and we identified some parameters that significantly affect the privacy loss fitness for use trade-off that would need to be tuned further. Next, we worked with Rachel's team to elicit fitness for use requirements and help them visualize and analyze the privacy loss and fitness for use trade-off. And then we iterated on this process and made adjustments to the proposed algorithm. And then eventually, and this is still ongoing, we finalized the requirements and the algorithm. All right, so now let me tell you about some of the specific tools and techniques that we use. All right, so first let's define the problem a bit more concretely using this example. So for each combination of geography and detailed race and ethnicity group, we want to produce a total count and a breakout by age and sex. So each record has a GeoID, which determines its mapping to a number of geographies. It has a sex, an age, and a set of race and ethnicity codes that together determine its mapping to a set of race and ethnicity groups. So for example, maybe this record is tabulated into these two tables, and then it contributes to the appropriate counts. So this was a female 81 to 84, so this count goes up and then also contributes to the total. And some just additional criteria that influenced our algorithm design. So first, we mainly care about relative error. Second, we care about some of the intermediate breakouts, so not the full age by sex breakout, but we also care about, for example, just the breakout by sex. And then finally, the statistics should be integral, but there are no other consistency requirements. Okay, so here's like the most basic differentially private algorithm that you could think of to solve this problem. So for each statistic, we'll just add Laplace noise scaled by the sensitivity. So this is discrete Laplace noise instead of Laplace noise because these counts need to be integral. But if you haven't heard of the discrete Laplace distribution, it's similar to Laplace. Okay, so then starting with this baseline algorithm, we present a series of modifications to get to the algorithm that we have ended up proposing. And so I'm only going to present sort of the major changes. There are some minor things that I'm leaving out. Okay, so optimization one is that we want to be able to adjust the privacy budget separately for separate race and ethnicity and geography levels. So the geographies can be divided into levels. The race and ethnicities can also be divided into levels such that the sensitivity, so the contribution of one record within each level, is much smaller. So this by itself doesn't reduce error, but it allows us to tune the privacy loss separately for separate levels. And this is good for two reasons. One is that we care about relative error, so we can give more privacy budget to smaller groups that we expect to be smaller, and less privacy budget to groups that we expect to be larger. And so this sort of optimizes the relative error. Second is that we can, with feedback from stakeholders, identify some groups that we want to give a lot of privacy budget to. So for example, if we've decided that all of the counts at the nation and state level are really important, we can give much more privacy budget to the nation and state counts. Okay. Optimization 2 is that we adaptively choose the statistics level using a fraction of the privacy loss budget. So we define 4 statistics levels. So total is the total count of the group. Sex cross age 4 buckets is the sex cross age breakout where age is grouped into just 4 groups, et cetera. And these statistics levels are separated by thresholds that determine which statistics level we want to compute based on the group's size. So we get some group, European California, size 21,000. Clearly, I didn't think enough to make this a realistic example. We use some privacy loss budget to get a noisy size of the group, so maybe it's 19,000 in this case. And then based on the thresholds, this gets mapped into the sex cross age 4 buckets, and then we use the remainder of the privacy loss budget to calculate the statistics at that statistics level. So we do this so that we can larger groups, we can compute more detailed statistics, and smaller groups, we can compute less detailed statistics. So this is the second idea. All right, and finally, we use the discrete Gaussian mechanism and ZCDP privacy accounting. So there's a lot to unpack here. I'm going to give you a really brief overview, but I don't have time to go into details, so if you want to follow up with me, feel free to do so. All right, so first, the discrete Gaussian mechanism. This is almost exactly what it sounds like. It's similar to the Laplace mechanism, but you add noise from a discretized version of the Gaussian distribution rather than the Laplace distribution. Now, the discrete Gaussian mechanism doesn't satisfy pure differential privacy for any epsilon, but it does satisfy this thing called zero concentrated differential privacy, or ZCDP. So I won't give you the definition, but sort of the important takeaway here is that this is an alternate privacy definition, and it can be converted into approximate differential privacy. And second, this performs really well when we're composing many queries. All right, so what do we find? Well, if we fix the margin of error, then the privacy loss under pure DP compared to the privacy loss under ZCDP is moderately better if we use the discrete Gaussian mechanism and ZCDP. So there are some caveats here. Number one, remember that these are not the production values, as a reminder. And number two, these aren't completely comparable because the first privacy loss, the 15.3, is pure differential privacy, and the epsilon of 12.2 is approximate differential privacy with some small delta. But we chose this delta to be really small, so we think that this is fairly comparable. And then another thing to keep in mind is you can choose a larger delta that's not quite as that's not quite as conservative, and then the gap in privacy loss is even larger. All right, so this is the third idea. If you're composing many queries, ZCDP is often a better choice than pure differential privacy. Thank you.